Hello, welcome to another coding vlog, and in today's video we're going to have a look at streaming calculations for quantiles. And it's all based on this paper that I have right here on the screen, the p-squared algorithm for dynamic calculations of quantiles and histograms without storing observations. So in this video we're going to go and implement this. Now, one reason why this caught my eye was because within the Python scientific libraries, at least, the big ones like scikit-learn, there isn't really an implementation for how you might calculate percentiles in a string. Now, there may be implementation reasons for why it's not done, but it's certainly not because algorithms don't exist. And I can think of a few reasons why the implementation might be a challenge, and I may or may not cover it in the video, but if you are interested, do leave a comment. So the gist of this algorithm consists of a couple of points. It's an approximation algorithm, right? And it does so by keeping track of what they describe in the paper as markers. So you want to keep track of the min and the maximum, which is fairly trivial to do over a stream. But you also want to keep track of the index of where the particular percentile is. So if percentile is p, you want to keep track of p, and you want to keep track of p divided by 2. So between the minimum and that percentile, and also between the percentile and the maximum. So 1 plus p over 2, or 100 plus p over 2, depending on whether you're defining percentile to be a number between 0 and 1 or 0 and 100. And if you manage to do that, then you can use these markers to interpolate what the approximate percentile is through updating information over a stream. And it outlines this approach in this paper. So I'm going to jump straight to the algorithm because this is what we're going to be implementing. And I'm not going to go through the detail per se, but I'll just talk through the ideas. Okay, so firstly, the first thing is that if you read the algorithm, there's two parts. There's a part A and a part B. Therefore, two different kind of scenarios, and the two different scenarios are fairly intuitive to understand once you get a gist of what's happening. So for part A is for initializing this algorithm and for the first 5 observations. So when you only have 5 observations, then you do what you can. But this is all the buffer requires, and one of the reasons is because the number of markers, as I sort of alluded to, is 5. So they need to keep track of at least 5 values, 5 markers, in order to actually kickstart this algorithm. So essentially, if you have the number of values that you want to calculate a percentile to be less than 5, then this algorithm doesn't really do you any good. But when you start increasing it to be over 5, then there's a way to update the particular percentiles in a stream-like manner. All right. So let's have a look at how you initialize the values. So firstly, you pick the marker heights. So the marker heights is basically the observed values that you have in the string. So essentially what this is saying is they've called the markers to be an array called Q, and these are sorted, right? So they use an index of 1, but I'm just going to use 0 because Python is 0 index. But so Q0 would be the minimum value, Q4 would be the maximum value, and you just go and update it in that way. Now for the marker positions, these are integers, right? So these indicate the index. It will become more apparent in terms of why they're doing this, but they just select the index to be 0, 1, 2, 3, 4. Keep in mind I'm using 0 indexing. Right. And then what we want to do is we want to get a desired index position. Now, where these marker positions are integers, right? So firstly, the marker heights, they are real numbers because these are assignments. These are the observed values in the string, right? For the marker positions, these are indexes, so these are integers. Now the desired marker positions, these are floats, right? And they're defined thusly. So they've defined a percentile to be a number between 0 and 1. And hopefully I'll remember to switch between the two definitions, because if you use Numpy Percentile, they define percentile to be a number between 0 and 100, right? So how they've done it is there are these desired marker positions. So these are marker positions based on what you've seen more or less, or like the observed values, and these are floats. So it's suggesting that the very first marker position, well, this is 0 index. The last one is 4, and the desired marker position, depending on what you've seen so far, will be roughly these few points. Remembering that we want to the first point is minimum, the last point is a maximum. The second point, so this point here will be between the desired percentile and the minimum, so p over 2. The middle point will be the percentile itself, and the last point will be between the percentile and the maximum, right? And this keeps track of where in the index it is. You can convince yourself that these maths make sense, but I'm going to skip that for a lesson for later. All right, so then once you've done that, there is then the increment, right? So this is a desired marker position, these are the marker positions, and then this is how you increment the marker position. So D in this case is the side, plus minus 1 depending on where the values corresponding to these markers, whether they lie above or below. And this just shows you or tells you how over time how we increment the various markers. So these are fixed because P is known. P is a fixed value when you initialize the algorithm, and all of these can be calculated and initialized. So that's part A. Okay, so then for part B, it's like, okay, once I have more than 5 observations, if I have the 6th observation, how do I update all of this information? All right. So keep in mind, just to reiterate, the actual percentile that you want to calculate in terms of the markers will be the Q2 if you are doing 0 indexing, or Q3, because again, the lowest one is minimum, so Q0 is minimum, Q1 will be the halfway point between 0 and the desired percentile, then Q2 will be the actual percentile that you want, Q3 will be between P and the maximum, and then Q4 will be the maximum, right? So remembering the thing that we actually want to keep return at the end will be Q2, and this is a saying, how do I update all of this information whenever we get a single observation? So let's go through this and think about this very quickly. Let's look at the first case and the last case first. So the first case is if the incoming value is lower than the minimum value, well, that's pretty easy. We just update the minimum value. If the incoming value is greater than the maximum value, right? So this is the last case, then we update the maximum value. That's pretty easy. And all of these Ks, well, we can ignore them for now, but just keep these in your tabs in terms of what they look like. So it gives a hint in the next one what the Ks refer to. So it says to increment position of the markers K plus 1. So what these Ks really are is they are indexed to indicate what is the next thing that you need to update, right? So for example, if it lies between a particular value, then we need to update all the markers that are above that value, which is why they have K to 5, or in this case, K to last index, where the 0 index will be 4. And we just we increment all the markers. And in a similar way, we update the desired positions for all the markers. So that's where this thing is. Right. Yeah, keeping in mind D is the sign. So if it is below, then it'll be a negative. If it's above, then it'll be a positive, right? So that's where this D comes into play. Remembering again that this thing here is a float, and this thing here is an integer. Right, so now I've updated the various values. So what remains is I need to update Q somehow. So I'll update Q by interpolating based on these indices. So there's a fixed formula here to show you what it is. If you read it, then you'll begin to understand what it does. So if D is equal to 1, that means that this is on the positive side of the marker, and if D is less than 1, then it's on the negative side of the marker, right? And then this index here just verifies whether it sits in that particular area or not. Right, so if this is true, if these conditions are true, that is that this particular range should be updated, then they have two different ways of interpolating. So one, they interpolate using some kind of parabolic formula, which is shown in this paper. I'll show it to you very briefly. I think it is up here. It's over here. This is a parabolic formula. Or they have a linear interpolation, which I won't really talk about, as you'll probably be able to you will easily be able to find out what it is. So if these conditions are met, then you update the corresponding indices and markers, and you can see that this becomes the interpolated value that you want to have. And then at the end of all this, then you return Q3, or Q2 if it's zero index, is the current estimate of the quantile. So all of this is how this algorithm falls together, and we're going to try to implement this in Python right now. All right, let's get implementing. Okay, so I've already done this on the side, but it's worth going through line by line what I'm actually thinking, and rather than doing it from top to bottom in the code, let's just try to do things in a way that is more conducive to how you might program. So what I want to do is let's start off by just using NumPy library, because that's pretty normal. And what we want to do is we want to make it look something like scikit-learn. So I'm going to call it approx quantile for now. I said to look like scikit-learn. I'm not going to do it exactly, but let's just start off by with some definitions. So I'm going to use p to be between 0 and 100, because I think that this is easier if you're coming from NumPy, and then just to say that you have equivalent definitions. And what I'm going to do is let's just update this as an attribute in two ways. So one way to be representative of what is in the paper, which will be p over 100. P over 100, and the other way to be what we're used to seeing as NumPy users. Next thing we're going to do is, if you look at the algorithm, I'm going to initialize the qn. I'm going to initialize the arrays of q, n prime, and also the dn prime. So one thing before continuing, actually, that I probably need to preface this, and I'll put it in the description, is a lot of the work that I've done was actually based on reading a particular blog post where this was implemented in C++. I've made some changes, but I will link you the original post in the YouTube description box. All right, so this is just to make things look similar, and to start off with, let's just initialize everything to be none. Now we can do a better job, but for simplicity's sake, let's just do it this way. We can do a better job because if you know what the p is, as in the part A block, you can already initialize all of this from scratch. Equals none, and self.q equals none, and we're gonna need a way to initialize it, and I think the best way is just to use a reset. I think the idea of using reset is more from like reinforcement learning if you ever code a gym environment, which maybe I'll do next time. But let's just play around with this idea first. So let's initialize our markers 0, 1, 2, 3, 4. I want to use a 0 index, and I'm actually just going to copy the next bit, because the next bits are just exactly taken from, and sorry, I'm going to need to make this presentation mode, exactly copied from the paper. Right, so let's have a look at the paper again. We can initialize these. They have 1 to 5. I'm going to make a 0 to 4, and then you have exactly these kind of formulas as you have here. So all of these things are exactly the same, and same with the D and S down here. I've initialized Q to be empty because we haven't seen any data yet, so there's no point worrying about that. All right. Okay. So now that we've done that, let's think about the interface that we want. We want something that looks like this. We want self x, and I'll just make it y equals none for now. Return self. What we want to do as the output is we actually want to give a score. We want to give a score of what is the percentile given what we've seen so far. So let's start off by saying, let's make this easy for us. Let's go on and say, let's just pretend that we do have a score and we do have a fit. And think about how we might do this. So the paper suggests return self.q2, but we have a problem here because if q is empty, then what do we do? So let's just add some conditions. If length of self.q is less than 5, then maybe we want to do something, return none for now. Let's just have it return none. But I think there's a few other cases that we want to check. So such as, if, and I'm doing this because I know that there's some weird edge case things that go on, but I'm just doing this because I don't want to encounter them when I'm writing some of the code up. So if the actual value that we've seen is the minimum, then we actually want to return self.q0, and maybe actually this should be above, or maybe if this length is equal to 0, let's have it like that. Then return none, and then I'll change what this one looks like later. Else if self.p is equal to 100, so this is a maximum. We actually just want to return the last value, right? So q 4. Now, what do we want to do if it is less than 5? Well, if it is less than 5 but greater than 0, that means we have 0, 1, 2, 3, 4. We actually just want to select the index that's closest to the percentile that we want. So let's do something like, it's fairly easy in terms of what it looks like. You want to say what's the length of the number of elements that you have times the the percentile. So this will be whatever this number is, and we want to take the integer because then this will give us the this will give us the particular index that we're after, because we want to take the lower one, and then we just want to return self.q target index. It's pretty straightforward. So already we have a way to score now, and this should make sense. Let's check that this makes sense first, right? So let's just do a really naive kind of view, and that is what do we want to do? If self.q length self.q is less than 5, we want to do self.q.append. Oh, actually, no, I don't want to do it this way. So this is an array. Let's make our lives a bit easier, and I'm going to implement something called partial fit. And this is for a single value. This updates for a single value only for our sanity. Right? Let's say that we want to do a If it's less than 5, we want to append. And then we want to also sort this, right? Because if it's not sorted, we're going to have a very bad time. Return self. Okay, so that's at my partial fit, and I want to have this call self.partial fit x. And let's just, and actually self.reset. That becomes a bit more easier. So if I call fit, I actually just want to reinitialize and set and reset everything, and then call partial fit again. But sorry, but if I want to just call a partial fit to update, then I don't want to do a reset. So let's also define what the partial fit looks like. So partial fit is for x in x. I just want to call a self.partial fit for the single value so that I don't have to worry too much. Okay, so this is our initial implementation, and it doesn't implement the algorithm yet, but let's just double check that it works. So I'm gonna, by default, it selects a median, right? Approximate quantile. So let's have some cases of range 10. Score. Now let's think about what we expect this to return. So this stops when we get more than 5 elements. So we're just going to get 0, 1, 2, 3, 4. If I run the first one, it should return, it should print 0. If I take the median, it should print maybe 2. And if we want to print the maximum, then it should be 4, even though this element is of range 10, because it doesn't do anything if the length is greater than 5. So I hope that works. Yeah, 0, 2, and 4. So this looks like it's working as expected. All right. Now let's go and implement things for if it is more than this. Well, firstly, if it is less than 5, it just returns self because we don't want it to, and this becomes like sort of like a else. Well, we don't have to do that. So let's talk about how we're going to implement the next steps. All right. So if we look at the algorithm for a moment, so far we've done everything in block A. And maybe I'll make a note of that. We'll say that this is, this bit is part A of the algorithm, which is great. Let's go to part B of the algorithm. So we've done with part A. It looks like it somewhat works, at least. And let's go and have a look at what we have to do. So there's a number of cases that we first have to do. And I'm just going to copy and paste what I've already written. This is pretty boring in terms of what it looks like. If it is less than the minimum value that we observe, or it's a new minimum, it's greater than maximum, it's a new maximum, and then we select a particular k's. Remembering that if it is in between this k value, then we increment all the markers, right? So that's the first bit. This is what number 1 does. So this is step 1. Now let's go to step 2. Step 2. So we'll look at what step 2 does. Increment position markers k plus 1 through to 5. So it goes from I equals k to 5. Well, this is pretty cool and easy to do in Python. So let's have a look. And then we do these for these two things. This actually looks just like this. Okay. So we go from k plus 1 to 5. So if you're not familiar with this notation, yeah. If you're not familiar with this notation, then it's k plus 1 because there's a plus 1 here. Then this iterates. So if k is equal, so if we go range 2, 5, then you'll go from then this will return a list that is 2, 3, 4, and this will return a list that's the equivalent of 0, 5, right? So that's step 2. It's pretty straightforward if we look at the paper. Step 2. So the next thing is we have to implement step 3, which is probably the hardest bit. So step 3 is for I equals 2 to 4. So everything beyond the min and the max. Because the min and max, if it is the min or the max and it's already been updated, we don't have to do anything. Instead, we're interested in everything in between. So let's go and start that. So step 3 for I in 1, 2, 3, because 0 and 4 are the min and maximum of the list respectively in a 0 index case. And what we do is let's go ahead and start the first one. So the first line, we create a new variable called d, like that. And then if this statement is true, then we do all these, then we do this if, otherwise we don't. So I'm just going to copy the whole if statement because it's very long. And then we need to do stuff. So let's go ahead and try to read the stuff. So firstly is we select d to be the sign, and then we try the parabolic formula, and if it meets this condition, then we update, otherwise we use a linear formula. Okay, so let's write this in some kind of pseudocode, or not really pseudocode, but actual code, but we'll leave the implement details for later. So we're going to update the parabolic formula, which doesn't quite exist yet. All right, and if this condition holds, I'm just going to copy it, then we update, otherwise we run the linear. I'm just going to copy and paste, because there's not too much to it. Right, otherwise we use a linear formula, and then we update according to this, like this is the sign, right? So as we see here, or this. Yeah, keep in mind that this is a sign and not this thing here, because this is encased in the for loop. I mean in the if statement. Because if it was outside the if statement, then if this condition didn't hold, then maybe the di could be something that isn't +1 or -1. All right. Now for the next bit with the parabolic and linear formula, I'm not going to go into too much detail how that's done. I think it's fairly straightforward. So I'm just going to paste it here. And what I'm going to do now is I'm going to update this, and you can see that now we have the min, max, and also the median. It's not quite right, but we can ignore that for now. But instead, what I want to do is let's have a look at a real example in terms of a more real example of how we might use this. So let's go ahead. I'm gonna, for example, actually no, I'm gonna keep this example. So if I go ahead and go like numpy random.normal size equals 100. Okay. And I'm going to do x1 equals numpy.random.uniform size equals 100. And now I'm going to go x2 is equal to numpy h stack x and x1. Alright, so let's have a look at what happens here. And in terms of why, I think this is actually really cool. So firstly, if I do this, then we can get a summary of what x looks like according to my algorithm. So we can see that over the random normal, you get these three values. So this being the minimum, maximum, and this is the median. So because this is normal, it should be pretty close to 0. So it looks somewhat okay. We can do a Numpy percentile to have a better look as well, right? So let's go Numpy solution. What does this look like? So we have Numpy percentile x of p for p in I have 0, 50, and 100. Okay. Numpy says okay, the min max are the same, and we have the median, which is a bit off, but it still looks pretty good. Let's make this a little bit. Let's have this as P2 solution, right? And I'm going to change this to a list so that we can compare some other values. All right. So let's make this, why not, let's do a 5-number summary. And I know this is not the most sensible way of doing it, but bear with me. 4. Okay, there we go. Now we have the comparison of the 5-number summary. You can see that these are actually fairly close and pretty good. Now the amazing thing with this kind of approach is that you can stream in more data. Okay, so for example, just to show you that this works, let's say that I want to, what I want to do is I want to stream in the solution. So we're going to say that 5-number summary is equal to dot fit, right? So this will do a fit, and then I want to add in more data. So let's add data from x1. So then we're going to do s dot partial fit now, right, of x1 for x in 5-number summary, and then let's try scoring the I'm gonna do this in a new Jupyter cell just so it's clearer. Right, so now so just to recap, I'm gonna do a 5-number summary, but this time I'm gonna save it, And then I'm going to update it using different data from the uniform distribution. I'm going to compare this with what NumPy does it if I didn't stream it in. So let's change this to x2. And now I just need to do a score for this. And I'm going to do a partial fit. So this will do a fit, and then it'll do a partial fit. It will update it, and then I'll print out what the score is and compare the two. So hopefully it will update it and be pretty close. Oh, something's gone wrong. So let's have a look at what has gone on here. There's live debugging for you. So 5 number summary looks like that. I think maybe I have to 5 number summary. Oh, never mind. It's because I reinitialized the Percentile rather than using 5 number summary to score it. So that's actually my fault. So what I want to do is I actually want to do x.score for x in 5 number summary, and then hopefully it will get something that's similar. There we have it. So you can see that although it's not 100% correct, and in the blog post I'll link you, they do some comparison with other approaches, but you can see that it does pick up on at least the min and the max, and the medians look very, very close. You can see how that although it uses exactly the same object and just does a partial fit to update it, you can see how it has adapted to the new change in distribution of data. So just to show you that this works, let's firstly print off what the P2 or P squared solution is for x, and then let's print off what the P2 solution for x plus x1, or concatenated together, right? So there we go. We can see that these numbers in the middle are very, very different, or rather than 75th percentile is somewhat similar, but the median and 25th percentile is very different, and it's managed to, I guess, adapt to the changing context, or at least the median has adapted a fair bit. And yeah, this is just to show you how this algorithm can be used over a stream, and the usage of the partial fit kind of semantics that is in scikit-learn can be used to leverage these kind of ideas. I thought that this was a really cool algorithm to play around and think about, and I do encourage everyone to go ahead and try implementing ideas from papers that they may have seen, because it is quite useful in terms of learning new skills, and also thinking about how you may design and implement various algorithms. That's all I have. Hopefully you learned something, and I'll see you next time.